So in this video, I'm going to talk about Spiro's conjecture. Spiro's conjecture. Okay, so let's give the setup. So Spiro's conjecture is on the surface about elliptic curves. So S is going to be a one-dimensional scheme. It's going to be normal and irreducible. We're going to let K be the function field of S. And we're going to let E be an elliptic curve over K. Okay. And so what we're going to define is, now associated to this, we're going to define the kind of divisor form of the conductor. Form of the conductor. Okay, so conductors are really messy because there's lots of different ways to define them. And so I'm just going to make some temporary notation. This is non-standard. So the conductor of E over K is going to be equal to some divisor. And we're going to sum, okay, so this is the underlying topological space of S. And so we're going to have some numbers here, Fs and some number S here. And so these are going to be codimension one subscheme, so they're going to be divisors on S. Okay, so it's normal, so this makes sense. And then these things here are the conductor exponents. This is a conductor exponent. And there's many ways to define these. So let me just say that it's going to be like this. So E is going to be 0 if E has good reduction at S. 1 if E has semi-stable reduction at S. And then it's going to be bigger than or equal to 2 else. So this is going to be when it has worse reduction. So the picture to think about is the following. So like you have S here, and then you have your family here, and you have many sorts of reductions. So here, this is this case. This is Fs is equal to 0. This is where it would be equal to 1, and this is where it would be equal to 2. So this is a cusp, and then here's a node here. So that's kind of the idea. Both of these cases are the kind of the bad reduction case. So what you do is you take like a spreading out of this over this, so you can get a family, E to S, and then you define it via these invariants here. And I believe that this has to be for a Weierstrass model. Okay. I want to make some remarks on conductors. Okay, so when S is geometric, so i.e. This is S is equal to a curve, let's say over a field K, which is algebraically closed, then in this case, Fs is always less than or equal to 2. So there's at worst, additive reduction, usual additive reduction. Okay. And then if S is arithmetic, then there's a couple ways to define, there's lots of ways to define fs of ways to define let's say fs. Okay, so there's this og formula. So the og formula says that so it relates kind of the order of the minimal discriminants. So you take the minimal Weierstrass model, and then we'll have fs here plus the number of irreducible components of the reduction. So this thing's related to the neuron model minus 1. Okay, and then the other way that you can get it is from the Artin conductor of the Galois representation. So the Artin conductor of the field of the, so when you say of the Galois representation, you really mean of the field of the finite Galois representation on the p torsion. So this is at p. Okay, and so over Q, it's easy to define the p torsion. To define the p torsion for not over Q, I think you have to use these things called Serre twists. And so I think if we wanted to get into this, we would have to, talk about a lot more about conductors. And I don't want to go into this because it's a mess, and this is all really hacky right now. So, okay. So Spiros conjecture, what's the general idea? Okay, and it says that this delta E divisor. Okay, so you write down the minimal discriminant in terms of the divisor. It'll be less than or equal to something bounded. Okay, and so this should be for all elliptic curves, plus, and this depends on epsilon, so this will depend on epsilon in the field. Okay, so this is something here, and then we have 6 plus epsilon, and then we have the conductor divisor. So I'm going to put this in quotes because you need to kind of do variations of this. So like I said, in the case for number fields, in the case for curves fibered over another curve, you need to do different things. Okay, so this is the general idea of Szpiro inequalities. Is like so. Okay, and so now I'm going to stop talking about generalities, and I'm going to move to the arithmetic case. So in the arithmetic form, and now I can make this precise, of Szpiro. Okay, so here k is going to be a number is going to be kappa s, where s is equal to like spec of O of k here, and so this is going to be a number field, and then so I define this conductor star here, and now I can define the actual conductor. So it should be thought of as maybe taking some type of norm of the previous one. So the conductor of E over K is then going to be defined to be a product. Okay, so first, we have to set up a little more things. P, so P, then we have FP here. And this is going to be an ideal in OK. And when in the special case, when K is equal to Q, then here with the conductor of E over Q is going to be this product of P, and then we're going to have P FP's, and this is just going to be an integer. Okay, so we'll actually get an integer out, and now we can talk about some inequalities. So again, we're going to have the discriminant, and it's going to be related to the conductor here. And okay, so the Spiros conjecture is the following. It says that the maximum of the minimal discriminant in this C4 cubed of is less than or equal to, so this is saying for all epsilon, there exists some C epsilon such that for all elliptic curves over Q, we have the following. This is this times this conductor of E over Q to the 6 plus epsilon. So it kind of sucks that I'm kind of defining it like so, you know, like this kind of hacked together thing. But I mean, this is what it is. It is what it is. And I think when we do some more Arkelos things, it'll look a little bit cleaner and relate more to the geometric case. Okay, so what I want to show from this thing. So what's the point? So what do I want to show? Well, what I want to show is that this form of Spiros conjecture implies a weak form of ABC. Okay. This is exactly what I want to do. Nope. One finger, I guess. Okay. And how do we do this? So the method goes through Frey's curve. So a Frey curve. So this is like, if you've ever been seen from Oslo's theorem, the same type of thing happens. So so Szpiro is connected to ABC through Frey. And actually, the ABC conjecture actually implies Spiros conjecture as well. And this thing goes through, I think, this Hall's theorem, or the Hall conjecture. Okay, and so let me state this lemma that's due to Frey. Okay, and it takes a lot of space. Okay, so let ABC be coprime integers with A plus B is equal to C. Okay, and define the Frey curve, the Weierstrass form, y squared is equal to x times x plus a, x minus b. And so this thing is called the Frey curve. So we can call this, so this is an integral curve associated to the ABC. Okay, so this is this Frey curve. Okay, then so Frey, so we can explicitly compute the minimal Weierstrass model of the Frey curve. Okay, and I'm going to do this on the next page. Okay, so here's this. I wish I had a little bit more space, but I don't. Anyway, so there's case 1. This is when 16 divides ABC. And when 16 divides ABC, A is going to be congruent to 1 mod 4, and B is going to be congruent to 0 mod 16, without loss of generality. And then we have the following equation. So for the minimal Weierstrass model, so y prime squared plus x prime y prime is equal to x prime cubed plus a minus b minus 1 divided by 4, x prime squared minus ab divided by 16 x prime. Okay, so this is the first case. Okay, the second case is that 16 does not divide ABC, and in this case, the minimal Weierstrass equation looks like here x cubed plus a minus b x squared minus abx. Okay, and okay, so this is what we have, and here we can actually compute the invariance. So C4 prime is equal to a squared plus ab plus b squared, and delta prime, this will be the minimal discriminant in this case, so this will be abc squared divided by 2 to the 8. And then here, C4 is equal to 16 a squared plus b squared plus ab, and the discriminant here is 16 abc squared. Okay, so here we can actually write these down, and so I kind of want to indicate a little bit of how this is done. So the proof idea here is, okay, so let's look in the case, like in the case where 16 divides ABC. So that's the top one there. Okay, we transform the first equation. So the first equation is this Frey curve, the original Frey curve. Y squared is equal to x plus a x minus b. Let me see if that's right. Yeah, plus a x minus b via the so we just have, so it's kind of enlightening. So x is equal to 4x prime, y is equal to 8y prime plus 4x prime. Okay, so we just kind of make these change in coordinates and then use the formulas for discriminants. So again, if we have, if we had something, so I'm just going to write this out and maybe fast forward it. Okay, so we have the general form for a Weierstrass equation. Then we have the B invariance here, and then, for example, C4 is defined in terms of the B invariance by this equation. Okay, so what we do is we kind of just change, we compute this, and then there's a similar formula for delta. So okay, so I guess these should maybe be primed or something. But there's a similar formula for delta in terms of B's. And then you compute what happens. Then you compute what happens after an admissible change of variables. Because there's that theorem that says if we have another Weierstrass form, we know exactly that the transformations kind of look like this. Okay, so that's kind of the idea. So it's a big computation. Okay, so now I'm going to show that, so the proof that Szpiro implies a weak ABC. I guess not. Okay. Okay, so so we had the computation of what C4 was and what the delta was. So C4. So let's look at the So let's look at the case. 16 does not divide ABC. Okay, in this case, what do we have? So C4 is 16a squared plus ab plus b squared, and delta, so the minimal discriminant is 16abc. So this is the discriminant of the minimal Weierstrass equation, and so we can compute what the maximum of C4 cubed delta is. Okay, and so this is equal to the maximum of 16a squared plus ab plus b squared. This thing cubed, and then we have 16abc squared here. So this thing is bigger than the maximum of A, B, and C. You can see that even from the second component there, since they're all positive. And so by Szpiro, this is going to be less than some constant C epsilon times the conductor of E to the 6 plus epsilon. Okay, and so we can just do a little computation here that the conductor of E, well, this is going to be equal to, well, so in this case we need to kind of look at the minimal Weierstrass equation, and it turns out that this is going to be 2 to the f2, so whatever this is, times the product of p divided by the discriminant, and p does not divide 2, okay, and the discriminant is here, okay, so the part that does not divide 2 will be taken up over here, and then we have this ABC part, so this is really just p divides ABC. And what you'll have to see is that so what you see from the equation, that FP is going to be equal to 1. Okay, so it's going to have good reduction for P not equal to 2. Okay, and besides that, this is going to be equal to, so this is equal to, when we have this dividing here, so this is going to be 2 to the F2, and then we have the product, so let's say it's less than or equal to this, the product of P, where P divides ABC. Okay, so this thing's going to be bigger than this one, and then this is just the radical here, 2 to the F2, the radical of ABC. Okay, so what does this tell us? This tells us that this thing here, so we have this inequality, and so this will be 2 to the F2. Well, okay, so this will be C epsilon 2 to the F2 then I guess 6 plus epsilon. And then we have the radical of ABC to the 6 plus epsilon. Okay, and so what remains to be shown is that this F2 doesn't get out of control. But we made this comment that the conductor of E over Q divides the discriminant here. So, and then we have the other fact that we had, so this is equal to, so this is the same thing. This thing is equal to 16 ABC in this particular case. And so this tells us that F2, so we just need to look at the P part of this, okay? We also have, we have 16 does not divide ABC. This is the two conditions that we have, okay? So these two things here tell us that F2 is going to be less than or equal to, well, we have this part here and this part here, so we have the two parts. This is 2 to the 8th times, and then it's not bigger. 16 does not divide that, so this squared here, and so this is equal to what? 2 to the 8 plus 14 here, so this is 2 to the 20. So 622, right? Okay, so we have F2 is less than 2 to the 22. I'm sorry, F2 is less than 22. Sorry, plus. So, because 2 to the F2 is going to be the P part of the conductor, or the 2 part of the conductor. So, all right, so this is just going to be 22. And so what does this tell us? So this tells us, so if we go back here, that max ABC, A, B, C, is less than or equal to some constant that depends on epsilon, 2 to the 22, 6 plus epsilon, to the radical of ABC to the 6 plus epsilon. Okay, and so like if we take, so the Spiros conjecture was for, all epsilon. If we take, let's say, epsilon is equal to 1, right, then we get a form of ABC for, let's say, epsilon naught is equal to, so this is 7, so this would be epsilon is equal to 6. Okay, and so this depends on epsilon here. Okay, so this closes and this finishes the first part. Okay, so this finishes when 16 does not divide ABC. Okay, when 16 does divide ABC, okay, suppose now 16 does divide ABC, we're going to do something really similar. So here we had C4 prime is equal to A squared plus AB plus B squared. This thing here is equal to 2 to the minus 8 of ABC squared. And then we'll have here. So then we just kind of write it down again. So I'm just going to maybe fast forward here. Okay, so one thing that we need to know is that from the form of the equation, so let's go back to it. Here, let's see. We're in this case here. So here, we need to look at what's going on, okay? And so if you analyze this, you'll be able to see that here, at worst, you're going to have multiplicative. You're going to at worst have multiplicative reduction. Okay. 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 That the form has multiplicative reduction. Okay, so FP is equal to 1. Okay, which implies that the conductor of, let's call that E prime, is just the radical of delta E. So this is equal to the product of P's dividing this ABC squared over 2 to the 8th and P. And this is certainly less than or equal to the radical of ABC. Okay, so putting these facts together, we get that the maximum of ABC is less than or equal to the maximum of A squared plus AB plus B squared cubed divided by ABC over 2 to the 8th here is less than or equal to C epsilon. So this is the Szpiro step. The conductor of E over Q, 6 plus epsilon. And so this is less than or equal to, as we decided before, the radical of ABC, the 6 plus epsilon. Okay, and so plugging in, epsilon is equal to epsilon naught gives us a weak ABC. Okay, and so now we have two versions. Okay, and this is essentially how the Szpiro conjecture implies the ABC conjecture. All right, thanks for watching.